Okay, so I gave this talk earlier this year, and it was a 2-hour workshop, so I need to put my head down and go at about 4 times the usual pace. But we'll get through it together. Okay, so this talk is about programming safely in an uncertain world, which is the world in which we all program. So we're going to start by launching the REPL and bringing in a couple of dependencies. Sanctuary and sanctuary def. And we'll be using these a lot, so I'm going to unpack nothing and just. Okay, that's all we need for now. Let's have a look at a function. So s.words. If you just type in any function name into the REPL, you'll get back the type signature. So we can see that words takes a string and returns an array of strings. So let's check that it really does do that. Great. So we've used a function. Yes, no surprises so far. Okay, this is very quick, but this is an algebraic data type. This is a definition that you would see in Haskell. We're defining the bool data type, and it has 2 data constructors, false and true. And so we can see that false is a member of the bool type. True is also a member of the bool type. So that's one that you're familiar with. This is one you might not be familiar with. This is the definition of the maybe type. And so we say that to create a value of type maybe A, we either use the nothing data constructor or we use the just data constructor. And you'll note that the just data constructor is parameterized. We need to provide a value of type A. So nothing, that's a value of type maybe A. Just 0, that's a value of type maybe number. Okay, let's have a look at a function that uses that type. So Sanctuary has a parseInt function. Here we have parseInt is a function that actually takes 2 arguments, but 1 at a time. So this is a curried function. All functions in Sanctuary are curried functions. Let's actually use parseInt to parse a base 16 string. So let's try one that is valid. And we get back the result, and it's inside a just. And the just tells us that that computation was successful. If we try something that isn't a valid base 16 string, we get back nothing. That tells us that the computation failed. For comparison, let's try the built-in JavaScript function with those same 2 inputs. So parseInt with the FFFF succeeds. We try an invalid input. We get back nan. So similar, but you can see that because we don't have the extra context, we're not able to describe success or failure. We're forced to resort to this bogus value. So the maybe type saves us from throwing exceptions, and it saves us from using these bogus values that we should avoid. The maybe type answers this rather philosophical and pointless question: what is the first element of an empty array? The answer is obvious once we look at the type signature. Head takes an array of elements of type A and returns a maybe A. This is obvious when we consider that in this case, we're not providing a single A, so we have to return nothing. If we pass in foo bar baz, we'll get just foo. It makes sense. No more undefined, no exceptions. How do we operate on a value inside a maybe? It seems difficult because we put it in this context. It's actually really simple because we do this all the time with arrays. So we're familiar with mapping over arrays. So we can, let's subtract 1 from each of these values, and we get back 0, 1, 2, just as we would expect. All we need to do is change the input. Let's try mapping over just 100, and we get back just 99. No surprises at all. And we can map over nothing, and we get back nothing. So far, so good. And one way to get an intuition for this is that nothing is equivalent to empty array, if you squint, and just 100 is equivalent to a singleton array that just has the value 100 inside. We could do those same mapping operations, and we would get back either empty array or a singleton array containing 99. So yes, map is very general. We can even map over string maps. This would give us back x0, y1, z2, just as you would expect. So let's have a look at the type of map. Okay, we're not going to delve into the meaning of this functor, but just look at this and you'll see that it's a very general type signature. We're not hard coding a single type anywhere. So what I find helpful is to actually specialize these general types so that we can get our head around what this is actually going to do for us in practice. So let's replace all the A's with string, let's say. Let's replace all the B's with integer. And let's replace all of the F's with array. And let's see what that gives us. So this tells us that if we want to use map in this way, it can be a function that takes a function from string to integer. So that might be the string length function. It takes an array of strings, and it gives us back an array of integers. That's great. But what's so wonderful about this parametricity is that we can substitute something different in the place of f. And look, that same map function is doing something very different. It's operating within the context of a maybe. So that's why we're able to use this function in these different contexts. Function composition limits complexity. It is the method of limiting complexity in our programs. It's also central to the Sanctuary experience, just for a joy of programming reason. So the way that we compose is usually using the pipe function. So what pipe lets us do is provide a foldable of functions, such as an array of functions, and thread a value through all of those computations. So let's try this. And we gave it no functions to compose, so obviously it just gave us back the input. But let's try doing something more interesting. Let's start by getting the words. Okay, now we have these 3 words. But let's add another step to the pipeline. Let's now map over those words, and for each word, let's access the length property. So now we have the lengths of the words of the input string. Let's go a bit further. And you can see that this style of programming, particularly when you're writing in a text file rather than in a REPL, is very fun because it's just adding one computation and getting immediate feedback. So this time, let's also map and get the square root of each of those. Okay, and as a final step, let's get the sum of all of those. Okay, so that's how we compose functions using Sanctuary's pipe function. You can see the type changing here. We have A to A. Now we have string to array of string. The type is changing as we compose more functions. Now we have a challenge. Let's create a 2-dimensional array of all the words and all the lines of a string. So let's make a string. Let's go with 1A, 1B, 1C. New line, and then let's just go 2A, 2B, 2C. And let's go with just 3A, 3B, something like that. Okay, so we can use Sanctuary's lines function. Works very similarly to words, but it operates on lines of text. Okay, so we have now an array of lines. We want to operate on each line. So let's map and get the words of each line. Okay, so we now have this 2-dimensional array. We've solved our challenge. So question, how would we go about creating a 1-dimensional array rather than a 2-dimensional array? Let's have a look at this join function. This has nothing to do with array join. It's a very different thing. And we can tell when we look at the type signature. Let's not worry about what a chain is. But again, let's try specializing this type. Let's replace all m's with array. So you can see that we have a function that gives us a way of taking a nested array and removing one level of nesting. This is not flattening, this just removes one level of nesting. Similarly, let's try replacing array with maybe. This is getting quite repetitive. You can see that these functions are very general, and we can use them with arrays and maybes interchangeably. OK, so this can solve our problem, because we can come back to the code that we wrote before. This gave us the unwanted nesting, and we can use join to remove it. Now we have a one-dimensional array. That's great. Here it is written using pipe. But instead of mapping then joining, we could have avoided the unwanted nesting by using a more precise function. And that function is chain. This is sometimes called FlatMap. And if we look at the type signature, it's very similar to the type of map. And let's try to specialize this to get a feel for it. So let's say we're going to replace all occurrences of A with string. We'll replace all occurrences of B with string. And we'll replace all occurrences of M with array. Let's see where that gets us. OK, so looked at this way, chain takes a function from string to array of string. It takes as its second argument an array of strings, and it returns us an array of strings. Now, why is this a perfect fit for our use case? Well, what's the type of s.words? String to array of string. This exactly matches the type that we can give to chain. So if we chain with the words function and give it the lines of text, we get back the one-dimensional array that we wanted. So it's FlatMap. That's a good way to think about it. OK, so you can see that what we've done is we've replaced what was two operations, this map plus join, with chain. And the wonderful thing about programming with laws, that's a word I haven't heard mentioned too many times in the last 2 days, but laws are a wonderful thing. Once we have laws, we can refactor with confidence. We know with certainty these two expressions are equivalent. We can always replace map plus join with chain. Flat mapping allows us to chain together operations which may fail. And there are so many different types of failure that we deal with every day in our programs. So here's a challenge. Get the first element of the first element of a two-dimensional array. This sounds so silly that we almost don't need to write any code. So let's define this array of arrays. Let's call it happy. And we've solved the problem. OK, so I'll move on to the next thing. Actually, let's just check another couple of things first. Let's create a second test case, and let's see how this works. OK, so that's undefined. Maybe undefined is OK, though. We'll just let the next thing in the program crash and say it was their fault. But let's try sad. OK, so that's clearly not a good solution. So let's think about it. Let's try to get the head of happy. Great. OK, what can we do with a maybe? Well, we know that we need to operate on the value inside the maybe. How do we do that? The first thing to reach for is always map. So let's map over the result and get the head of the result. OK, but we introduced unwanted nesting. So what we wanted was chain, and we have the solution. And what's lovely is that the head function has forced us to handle the success case and the two distinct failure cases. So unhappy just works, and sad just works. So there was no way to forget to handle the failure case. We were forced to handle it by the descriptive value that we were given by the head function. So here it is with map and join. Here it is with chain. So it's just two very simple steps. So yeah, chaining over nothing is going to give us nothing. In this case, we have an array, but the head operation fails and gives us nothing. And in this case, we have an array, the head operation succeeds, and we'll get back just 13. PauseJason is another operation which may fail. So let's prove it to ourselves. Let's parse some what looks like incomplete JSON. Let's see what that gives us. Unexpected end of JSON input. OK, so Sanctuary never throws exceptions unless we make a programming error. OK, so PauseJason. It takes some predicate that we'll get to in a minute, and a string. and it returns a maybe A. This is not a very helpful type signature, but let's have a play with it. So let's give it a value that satisfies the type signature, and let's try our invalid JSON input. Okay, we got nothing. So say goodbye to try-catch. We never, ever want to use try-catch in our programs. Okay, so that was great. Let's try making this valid, and now we have the result. So far, so good. Now we're going to have a brief look at some functionality that sanctuary-def provides. So we're going to ask whether this value is a member of the integer type, and it isn't. But let's try changing this to something that we know to be an integer. Okay, so that's neat. Nothing too crazy there. But this is where it starts to get really nice. We have the ability to describe types in real detail. So we can ask whether this value is an array of integers. So let's try this. So that's not an array of integers, but let's try this. That is. So that's really sweet. Now let's come back to PauseJason. So that predicate that we ignored initially is actually really helpful. So this predicate allows us to place a constraint on what we will accept as a valid value. So first of all, PauseJason will ensure that the parsing succeeds and will deal with any exception that may be thrown. And it will then give us the resulting value and allow us to do something with it. Okay, so we can say PauseJason, we can say, are you an array of integers? And then let's give it some input. 1, 2, 3. Let's make it valid. And we get back just 1, 2, 3. So we know that the type of this expression is maybe array of integer. We've dealt with all the uncertainty in one place at the very edge of our program, and we can now program with confidence, knowing exactly what we're dealing with. Lookups may fail. So I don't need to run these in the REPL. You'll all know what these will do. Yeah, lookups are a problem, not when dealing with code that we write, where we have control over the shape of things, but when dealing with input from other people. So Sanctuary provides a get function, which is specialized for dealing with this problem. So it's similar to PauseJason in that it gives us this ability to use a predicate to decide whether a value is valid. If, in fact, there is a, in this case, visible property, we're going to assert that it's a Boolean, and we'll get back, in this case, just false. Sequence is amazing. It has this type that is perhaps a bit confusing, but if we look at this type, if we were to specialize this, if we were to replace f with promise and t with array, we would have a function that takes an array of promises of A and gives us back a promise for an array of A. That's promise.all, but I recommend never to use promises. They are an abomination. But had they been well designed, we could have used our sequence function with them. So sequence, we can use it here. We're turning an array of maybes into a maybe containing an array. So this would give us back a maybe containing the array 1, 2, 3. This would give us back nothing. So sequence has this all or nothing characteristic that is going to become useful in this final challenge. So 5 minutes to go. Parse a given JSON string and return the sum of the elements at x, y, z if they are all hex strings. Okay, this is how we would do it in straightforward JavaScript coding for the happy path. We parse the string, we do the lookups, x, y, z, we fold, and we get back the result. But what are the problems? Well, this could throw an exception. That's a problem. This could throw an exception. This could throw an exception. This could throw an exception. This could actually, x, y, z could be there but not be an array, so there's no reduce. So this could throw an exception. We're assuming that it's an array of strings. S might not be a string. ParseInt might not like the non-string input we give it. This could be an exception. ParseInt could fail, give us nan, contaminate the whole computation. So we've got about 7 different failure cases here, and we are not handling any of them. So let's think about how we would do this the right way. So I'm really going to put my head down here and just go, because we have limited time. So, OK, we're going to do PauseJason, and for now, we're just going to say anything goes. And what we're then going to do is we're going to chain, and we're going to get, again, saying anything goes. We're going to get the x, and we're going to give it, oh, this is a challenge doing this quickly, but we're going to give it x, y, z. Never write JSON by hand, folks. 28, 29, and 20a. Let's try this. OK, so we have just this. It's going to get painful. We're going to have to do 2 more chain gets. So let's use some nice sugar. We're going to replace this with gets, which is the plural of get. We can then provide an array, and we'll provide the other 2 and see where that gets us. OK, so now we have this. Now we need to operate on those strings. They're inside an array, which is inside a maybe, so we need to map twice. So let's give that a go. So we need to do s.map of, in this case, s.sequence. Sequence, remember, is the turning inside out thingy. There's no way to describe it. I've tried. It's impossible. And let's see where this gets us. OK, this gets us to type error. So we can see here that I've made a mistake, and Sanctuary Def is providing us with some nice error messages in this case. But I see what I've done wrong, and I will quickly try to correct that. I got 1 step ahead of myself. So we first need to do the gets operation. We then need to do this should be the parseInt operation, base 16. And I think I have the right number of parens there. OK, so now we have this thing which is getting us closer. We finally need to use sequence to turn this inside out, because we have a maybe containing an array containing maybes. We want the maybes to get together so that we can join them out of existence. So let's quickly try this. We're going to chain. We're going to map with parseInt, and we're going to chain with sequence. And sequence needs this type hint. And I'm then going to actually just go ahead and do the final step, which is to take the sum of these values, and voila, just 1, 2, 3. So we've handled all these cases. There's actually one thing that I skipped here, which is this predicate should really be s.is $.array of $.string, and that guarantees that the value at x, y, z is in fact an array of strings, and that guarantees that all these future operations will succeed. So let's just step through it one more time. PauseJason, that handles the invalid JSON. We do these chained gets, which we can replace with a single call to s.gets. We can then replace this placeholder predicate with something that will assert that we have an array of strings and fail the computation if not. And by fail, I mean produce nothing, not throw an exception. We never throw exceptions. Then we can map over each of those strings, parse them in a way that is safe. And if any one of those strings fails to parse, we'll again fail the computation as a whole. We then use sequence, and sequence, look at this. We have a maybe array of maybe integers, and look what happens when we sequence. We now have a maybe of array of integer. And what can we do when we have nesting like that? We use our old friend join, and we remove the nesting. Now we just have maybe array of integer. And of course, we can replace map and join with chain. We've learned that already. And then we can map to get the sum. Now we have a function from string to maybe integer. Beautiful. And one thing you'll notice is there's actually no branching in this. You have 100% branch coverage without writing any tests. So that's pretty nice. This is the equivalent imperative JavaScript. We need to use try catch to do the JSON parsing. We need 3 null checks for the nested lookups. This is array check. And then we need to check that we're dealing with a string. We need to do some extra parsing to handle quirks in the built-in parseInt function. And we have to return nan explicitly in 3 different places. And moreover, our type is a lie, it's string to number, and we're using a bogus value nan. So Sanctuary, oh, that's meant to say refuge from unsafe JavaScript. Yeah, check it out at sanctuary.js.org, and I'd love to chat with you about it after this. 12 seconds to go, so good timing. That's it.
All right, we got a couple of questions for you. Ready?
Yes, sure.
What's that command line you're using?
That's called the node REPL. So all we needed to do to make this work, you might be wondering, how do we get these nice type signatures? If you specify util.inspect.custom, it's a symbol, then you can customize the representation of values when they're printed in the REPL.
How is nothing better than syntax error?
Oh, it's infinitely better. What do you do with syntax error? I mean, unless you're talking about actually just passing around an error as a value, which I haven't seen anyone do, I assume you're talking about throwing a syntax error. And, well, you can't compose functions that are throwing exceptions. And we want to compose, because composition is the solution to limiting complexity.
Next one, can you compare Sanctuary to Ramda?
Yes. So from 2014 to 2016, I contributed heavily to Ramda. There was a discussion specifically about the head function. Ramda's head function has the same problems that you know, the JavaScript sad example has, and I wanted to change that. There was some disagreement within the Ramda team as to whether we could push it this far. And in the end, I decided to create a separate library that at the time was just to accompany Ramda. But in the last 3 or 4 years, it's really become its own thing. And in many projects, I now use Sanctuary without Ramda. But they still work well together.
All right, next one. What is wrong with promises, and what would you recommend?
So I anticipated this question, and I recommend that you all read about broken promises. This is written by a friend of mine, Oldwin Vlasblom, and there are many, many problems with promises. Okay, you wanted to know what's wrong with them. Let's make this quick. Okay, they trigger side effects at the time that you create them. That's awful, because we want to actually just compose things and then trigger them when we're ready. That's one problem. So let me just look at the cliff notes. Eagerness, cancellation. Promises don't support cancellation. They should. There's a specialized API. So promises require us to learn all these promise functions. Well, if we learn Sanctuary and we learn map, chain, join, we never need to learn another API. We can go to these conferences and nobody needs to say anything about any API, because they're just providing types that satisfy these requirements, and we just use the 10 functions that we already know. So specialized API, thumbs down, promise.all, thumbs down. Yeah, no good. Error handling, I have no idea who came up with this, but the idea that a failed, an error, a programming error inside one of our functions when we're using then can somehow turn into a rejected promise is, well, diabolical, I would say, because we then have this, this possibility of saying, well, we're going to handle our error by responding to the user with a 404, because clearly the reason we got into this state was that, well, our database query failed, when in fact it was, you know, a typo in our own code. Every single user request coming in is just getting a 404 response. So, you know, programming bugs should crash our code. They shouldn't just silently turn into failures. That's like the nan thing all over again. Yeah, mixing exceptions with failures. That's really it. So, yeah, don't use promises. Oldwin has been working for the last few years on this library called Fluture. It's amazing. It integrates flawlessly with Sanctuary. And once you're using Fluture, you'll probably want to use PureScript, and really have all these tools.
Evidently very passionate about it. That's fantastic. All right, maybe time for one more question. How's runtime performance of Sanctuary? Is this all type system checking bringing too much computational overhead? Sorry.
Yes, it definitely does bring computational overhead, but we can turn it off. It's very simple. There's a create function in Sanctuary that returns a new Sanctuary module, and we can say check types false when we create that new sanctuary module. So we can even use a check like, node env equals production, then we'll use type checking, then we'll disable type checking, otherwise we'll have it on because we're in development.
All right, thank you very much.
Thank you.
Let's give David a hand.